in a sense. I'm sure that this is the first and last time I will record my lectures in optimization. So for example, next year, this service will be not available anymore. Okay, so when we increase the number of constraints, the problem gets trickier. So our cost function is f as usual. So it's some function which lives in n-dimensional space. So f is a function from Rn to R. It's real valued. And also the functions gk are functions from Rn to R. Maybe in some applications, the domain of definition of these functions is smaller. But in principle, we start that these functions are defined everywhere. There might be cases where for example, we restrict that the variables x or the coordinates of the x are restricted, that they are positive real values, real numbers. But in any case, we can consider also that case, so that in the same setting as we would define this function in Rn. But the main assumptions is we assume that these functions are differentiable, at least. And the second assumption is somehow silent assumption. So I assume that the functions are always, not always, but they are mainly convex. But I will present this constraint optimization in a way that it is immediately generalized to also to non-convex problems. We do not have time to deal with the problems which we encounter with relaxing the convexity. So there becomes serious problems to our theorems, which we have to somehow deal with when we have really non-convex. So mainly the functions are convex. So if we draw a picture of our, so we have the constraint set. Let's use some other color, for example, the color red for the constraint set. And then I use the color blue for drawing the level sets of the function fx. So every level set or equicontour line or equicontour surface is drawn with the blue. And in most cases, if we have this convexity assumption behind, we have the global minimum of the function located somewhere here. Which is of course outside our constraint set. And in convex case, we have already proved the criteria for finding a minimum point. So it was that if we take so we know already that in at least in convex case, we have the criteria that the function has a minimum at the point x bar when this inequality is satisfied. So the gradient of the function f at the point x bar, scalar product with the direction x minus x bar is greater than 0. So it means that if we go from the point x into any direction pointing into the set constraint set, this quantity the scalar product must be positive. So it means that the function values are increasing all the time. It comes exactly from the Taylor formula. So it's clear. And actually, this holds also for non-convex case. So if this is, we can relax the convexity. So we can say that this holds also for non-convex functions. What does it mean? It means actually something which is related to the cones. And let's define what do we mean by a cone. So cone is a set such that if you take a point in the cone and you multiply it by a scalar with a positive scalar, then the new point belongs to the cone, to the set as well. So obviously it means that origin is also, it belongs to the cone, because if we multiply any point from x with lambda equals to 0, then we are in origin, so origin must belong to the set. And if we take a direction, so if we take a point in the cone and the 0, so it means that this ray belongs to the cone as well. So starting from 0, we pass through the x, and then we can go to infinity. So hold the ray from 0 to x is in the cone. So then we have the typical picture what is meant by cone. So for example, here we take like here. So this is the typical picture what we have in mind when we speak about cone. So this is a 2D cone, it's just a wedge. And then if we make a rotation, it's the cone. But of course we can make the rotation in such a way that the angle is, for example, ellipsoid. So we might have here okay, now it doesn't work like this. So we might have something like this, and these blue curves are not anymore circles, but they are ellipses. So, and then of course it can be that these are, we have here, for example, for example, like this. This. So, and like this. And this is, oops. And this is how do I, it's better to draw like, so for example, a pyramid or tetrahedron continuing to into infinity is a cone as well. So the amount of shapes what you get for a cone is always, it's huge. These are examples of convex cones. So let's, I'm just trying to draw a better picture. like this. Then we might have non-convex cones. So for example, here, so this is a non-convex cone. So here is the same. If you take any point here and you join this one, for example, you join this one to origin, then of course you can carry out anywhere. And the same on the left, if you take a point here and you multiply it by some constant, then whole array is contained in this cone. Then the cone is convex if and only if the condition is valid. And the condition is that if I take any 2 points in the cone and take a vector sum of these points, then it is also in the cone. Meaning that if we take any positive numbers, lambda and mu, and x and y are in the cone, or in the set, or cone, of course, because we start with cone. And all this linear combination, lambda x plus mu times y, they belong to F as well. So if I take here any 2 points and make the vector addition, then they belong to the same set. But here, if we have a convex cone, so for example, if you take the cone here, so if you take the endpoints of these 2 blue lines and make the suitable addition, so the sum is somewhere here, it's outside the red area. So it is quite easy to see that the cone is a convex if and only if this condition F plus F is subset of F is valid. Then we consider closed cones. And it comes from our constraint set. The constraints are defined by the functions gk, which are by assumption differentiable. So that means that they are for sure, they are continuous functions. So the set where gk is less than x0 or equal to 0, it is a closed set. And that's the reason I limit our consideration that our convex cones are always closed, because our constraint sets are closed as well. Meaning that the boundary bounds are included in the set as well. And closeness means that if we have a convergent sequence in our space, so we have the sequence xk. Now k means xk is a point, so it has all, it lives in Rn. It's not a coordinate, and these points have a limit point a. Closeness means that A must belong to the set C as well. So we are not able to go out from our set by any limit process. So we have, you can imagine that this boundary is really a fence which prohibits you to leave this set. And then we start to investigate the cones related to our. So first the constraint set. I write here this letter capital S. In my slides, sometimes I have the capital letter U. It's I switch them from time to time. And I define the cone of feasible directions at the point U in such a way that it is the set I denote by capital letter C. And in parentheses, I have U. It is all the directions such that if I go from the point U into the, I add there t times the direction d, I remain in the constraint set. For some positive t between the interval 0 and delta is some positive constant. So for example, if I take, let's draw, we use red one for the constraint set. If I have like this, and I have here the point U, I have the, here is U plus t times d. So d belongs to the, for sure, now to the cone of feasible directions. I can take here an other direction. Here is also a direction which belongs to the cone. I can take, if we have a convex case, I can take any point on the boundary. I can take any boundary point and join it to the point U, and it is, the direction is once again inside the cone of feasible directions. So what is in this case? For example, I have here a smooth curve. What is the cone of feasible direction for this? We have just one function. It is the half space, because I can take any direction on the curve, on the boundary curve. These directions approaches the tangent line. So what we have here is the not very correct. I put it here tangent space because in Rn it's really a hyperplane, not the line. And all the directions in here are belong to the cone of the feasible directions. So if we have very well defined tangent at the point, then it's the half space. And half space is, of course, the cone. I have to, it contradicts our understanding that, okay, if I take a point here, it is outside our constraint set. But remember that in my definition, I have here that this number t is small. So if I join these together, then there are, at least in the convex case, there is some positive t that's from you, if you start into this direction, you are inside our constraint set, and so this direction is feasible. Then, of course, we have the cases if we have several constraints. For example, I can take, for example, I take a set like this. Okay, I have to a little bit. So I have a, for example, convex disk, and then I take, for example, I intersect it with a line like this. Okay, this was not, I should take only, okay. So we have two constraints. So for example, the first constraint is a circle constraints, for example, x1 minus a squared plus x2 minus b squared is less than r squared. And the other condition is, for example, that k1 times x1 plus k2 times x2 is less than some constant b. And then our constraint set is, for example, here. Now, if I take, for example, the point, I denote it with the blue dot here. What is the convex cone here? Or the cone of feasible directions? If I approach this point from the left, so to speak, I have there a tangent line. So I can draw the tangent. Something like this. And then, of course, the second one is because the other constraint is, let's say, we speak about linear constraints because it is defined by the linear equation or inequality. So we have here, oops. Like this. And now the cone of feasible direction is here. I have used the lilac or violet color. So now it's not anymore half space. If we have We can do it also for non-convex problems. So what about if the point is inside the constraint set? What is the cone of feasible direction? It is the whole space, because you can, if you are inside the constraint set here, for example here, you can go into any directions. So it's whole space. This cone is not necessarily convex. If we have non-convex problems, and of course this cone of feasible direction might be non-convex, but it is, to my understanding, it is always closed if the functions are, if the functions gi are continuous, then they are always closed. But if we have the functions gi are convex function, then for sure this cone is convex as well. Okay, then we have to divide the constraints in two sets. So those constraints which are active at the point and those which are inactive. So by meaning active constraint is those indices from 1 to m where this inequality is actually equality. So for example, if I take here a point here, then this condition, so that the point is clearly inside the circle. So we have, instead of, we have strict inequality here. But the second constraint is active because it's on the boundary of the half space, because it satisfies the condition that the equation of the line is satisfied. So one of the constraints is active and one is inactive. So to speak, if this point would be a minimum point, from our optimization point of view, we can relax this inactive constraints. It is unnecessary. But of course, in beforehand, we do not know whether it is active or inactive. Then okay, it depends on the problem. So for example, if I take lately I have been involved with the optimization problem related to the water distribution networks. So for example, you have a city and you have a reservoir. And for example, in Oulu, it means that we have in certain places, we have these water towers, which provide a certain pressure. The height or the water head, as the engineers call, it's something like 70 meters. And then we are building a new part of the city. So we have to distribute the water for every houses. Then I have an optimization criteria, for example, that I draw the pipelines. So there is the length of the pipes are the variables. The diameter of the pipes is one variable. Then I have, for example, the number of junctions. So there comes a pipe and then I distribute in different streets. Then there is a junction, the number of. But if we fix those things, so we have just continuous variables. So the length of the pipe, the diameter of the pipe, and then I have a criteria, for example, that the pressure in every part of the network is good enough. Then my variables are the length of the pipes, the diameters, and then I have a constraints. So because the pipes and the diameter defines that what is the maximum flow in the network, what is the maximum pressure in the network, what is the minimum pressure in the network. And then, for example, the problem is that I want to minimize the cost. I want to minimize the number of pipes and to minimize the costs. This is, for example, one. Okay, let's turn back. I defined the second code, C star. I define it by this condition that the gradient of the constraint function and the scalar product of it with the vector W is less or equal to 0 for every active constraint. So we fix the point U is in the constraint set, and I require that I consider those directions for which this scalar product is negative, or at least at most 0. So let's draw a picture. It is a cone. For example, if you take W, any W, and you multiply the W with the positive scalar, then the scalar product with the new point is still non-negative. It's non-positive. Because if we multiply, if I multiply this W with positive lambda, I can take the lambda outside of the scalar product. Lambda is positive and that scalar product is negative. The product is negative as well. So it's gone for sure. This one is also convex cone always. So if you take any 2 points, W and B, you take the sum of those vectors and you take the scalar product with gradient of Gi. The scalar product is also non-positive because you can split them into two parts which are both non-positive, and the sum of two non-positive numbers is non-positive as well. So this cone is always convex. Then the first theorem says that the cone of feasible direction is of course part of this cone C star. And when the main point is that when they are equal. So let us first look how this looks like, this cone C star. Because I want to prove that the C star is just another way of writing these cones of feasible directions, at least in the case when we have a convex optimization problem. For non-convex case, it is not necessarily true. It is easy to see that we have a non-convex problems where the cone of feasible direction is not the same as the cone of this C star. But anyway, let's take the convex case. We had here the boundary of our constraint set. I have now, of course, if I take the point inside, then the cone of feasible directions is always the whole space. But if I take the gradient here, so on the boundary we have Gi x equals to 0. And here if we have a z, it has the property that Gi z is less than 0. Because it is inside. Then you can go in by continuity. You can go into any direction, a small direction, and you still have, you are inside the cone of feasible directions. So if you take any point here, let's put it here, for example, this is z plus, it is z plus t times w. and you compute, you have sorry, there is this set. So I want to prove that this whole space is now, this one is I can take any direction. Okay, let's forget it, this one for a while, because we are interested on the points which are on the boundary. So for example, now I have the point U is somewhere here. I draw the tangent line as usual. And so we have the maximum point of this function in the constraint set is 0. Okay. And then it means that the minimum point of minus gi is at u. It says that then minus gradient of gi at u with any direction into the constraint set is like this. We are just increasing the values of the function when we go inside. So we are increasing the values of the minus gi, which is equivalent of saying that gradient of gi u scalar product with W is less than 0, and W is such that U plus T times W belongs to the constraint set for small t, which is positive. So it means that all points belonging to the cone of feasible direction, they must belong to this C star as well. So we obtain this theorem. And we can actually do the same thing for every. We just take another constraint set which is smaller than 0, and we carry out that one. So we get that in the interior points, every direction belongs to the set. There is whole space. But then the tricky part is that if these sets are equal, can we guarantee that one? And what is the condition? And the condition, for example, for the convex case is obvious that if I have here the grade, I draw the gradient of the function gi, where it points. Let's write it here. Gi x is here negative, and here gi x is positive. So on the left hand side of the tangent line, the function's values are positive, so they are increasing, and on the left hand side they are decreasing. So the gradient of the function at point u, which is on the boundary, is pointing here. Meaning that if I draw here the vector W, the angle between these two vectors is greater than pi over 2. So the scalar product must be negative. So in convex case, it's clear that this cone C star of U coincides with the cone of feasible directions. Because I know, for example, in this regular case, that the cone of feasible direction is the half space over here. And then it coincides with this C star, which it's the directions which form the angle which is greater than or equal than pi over 2. So it's over 90 degrees with the gradient of the function gi of u. And we have finite number of these constraints which are active. So it is for all of them the same. You just take the intersection and you. So in convex case, this theorem that these are equal is let's say, obvious. Sorry? Where? In convex case. Sorry, I have learned when I was child that write the capital letter I in that way. So sometimes it's okay, maybe no, my my teacher uh, 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 Anneli would kill me if he would see me writing capital I like J, like this. The next question remains that I want to a little bit generalize the result to more general constraint optimization problems. And I say that my constraints are qualified. Oops. If either the functions are affine, so we have a linear constraints. So we have the gi of x is a scalar product of a vector ai with x plus some constant. Or if the function is not affine, there exists a vector w such that for every active constraint, this w has a scalar product with the gradient of gi, which is non-positive. And if the function is not affine, the scalar product can be negative. In convex case, this is for sure. We have, in convex case, we have like this. If we take active constraint, this is not anymore an affine function. For sure, the gradient here of the function gi at u points into that direction. And then if you take, for example, because it's just beneath that there is one direction, which is in such a way that they are, the scalar product is negative, then I just take a small like this. And now we have here the scalar product is for sure negative. So in convex case, this is simple. But if we have a non-convex case, if we include this one, this type of functions in our constraints, then we have the theorem that Cu equals C star. So maybe I will put in this the proof of this theorem in the lecture notes. I noticed that there are several theorems which are at the moment without the proof, but I will include the proofs in at some point. So let's take some examples. So I have here drawn two parabola, so we have two conics. The other one is defined x1 squared plus 2 times x1 minus 2 times x2 plus 4 is less than 0. So it is this parabola opening upwards. And the second parabola is defined by the quadratic equation or inequality g2 of x is less than 0. So it's the parabola over here. And the intersection is here. It's actually, it is a bounded set because these parabolas are inscribing a bounded closed area, so compact set. And now we can investigate, for example, what are the these cone of feasible directions. And then I take a few examples. So for example, I take first yes. Yes. So you mean that, okay, I need these cones on Monday to prove what is the most important theorem in this course is the Karus-Kuhn-Tucker conditions. And I want to this time just draw pictures what are the cones look like, and they provide also the information that you understand the proof of the Karus-Kuhn-Tucker condition. So for example, I take the point with coordinates 4 and 6. Maybe I have to. So the point here is A. And I start with, so clearly the point 4 and with the coordinates 4 and 6, they satisfy the equation of the parabola exactly. So if you take x squared, it's 16, minus 2 times 4, it's 8. So 16 minus 8 is 8, minus 2 times 6, it's 60 minus 8, 6, minus, oh, sorry, there is missing, this should be 64. No, it's 4. Is it? Am I calculating correct? This is 16, 8. Yes, and minus 12 plus 4, it's minus 8. So it is 0. So this is really the point on the parabola. So on the boundary of the parabola. Then you can check that it is also inside the other boundary. So this constraint is inactive. If I want to find the cone of feasible directions, I draw the tangent line, because all the points on the boundary are now regular. It's a regular point of the parabola. I draw the tangent line, but now the tangent is actually, the tangent space is always passing through the origin. So remember that the cone passes through the origin. The tangent here is a transformed cone. When I draw the pictures, I sort of make a mesh out of. So when I speak about the cone of feasible directions, but I draw this one. So I have transformed this cone of feasible direction at the point where we are living in. But I speak all the time that we have go into that directions. So the cone of feasible directions is not this transformed cone, but it is the cone passing through the origin. So it means that it is here on the left. So you compute here the gradient of this function. I guess it was here computed. So you compute the gradient of the which was my function. Here should be actually 1. So if I compute the gradient of the function, or gi, it is so we had 2 times x1 plus 2. And the second is minus 2. and then you compute the gradient of the function gi at the point with coordinates 4 and 6. So it is 6 and minus 2. And then I should put it here. It's C. Oh. Okay, now they are. So now I can write this. So C star of U is the points or the directions Z. They have two coordinates Z1 and Z2, such that this 6 minus 2 scalar product with Z1, Z2, this is 6 times Z1 minus 2 times Z2 is less than 0. But then I can divide it by 2, then I get this equation here, 3 times Z1 minus Z2 is less than 0. So this is the cone of feasible directions, because the other constraint is inactive. For it, the feasible directions are whole space. And when I take the intersection of those two cones, it is just left with this one. This is the only cone which is really involved of the problem in that particular point 4, 6. The next one I take the point with coordinates 2 and 2. It is in the intersection of these two parabola. It's the point which satisfies both conditions. So it means that I draw the tangent lines for both functions. So I consider both constraints independently. And I first draw the constraints which relates to the first parabola, the GI. So the transformed cone of feasible directions is the half space over here, up the line. Then I draw the tangent line with respect to this parabola over here. It is this one here. And it is above this line. And then, because I have two constraints, I take the intersection of this cone of feasible directions. It is this wedge over here. So now I have here the cone of feasible directions. Of course, it is transformed because we should transform it so that this vertex here should be at the origin. So this is the mistake I make all the time, that I speak about of this cone of feasible direction, but I have to remember that actually the cone of feasible direction is located in such a way that the head or the vertex of the cone is at the origin. But I draw the pictures in such a way that it is the transformed cone. So here we have now the cone of feasible directions. And then we take constraint optimization problem. So I take a quadratic cost function. The level sets of these functions are ellipsoids. The origin of the ellipsoids is at the point 2, -5. So here I have drawn the level sets with different values of constants. So I require that this cost function fx equals some positive constant k. Here, because this is for every point not the center of the ellipse, this value is positive. So if I fix a positive number, then this defines an ellipse. They have exactly the same center here. And of course, the eccentricity is changing, but they are concentric ellipsoids or ellipses. And then, so to speak, I try to find the minimum of these constants such that this function or the level set touches our constraint set. So if the constant is bigger than this one here, then the ellipse is intersecting a large set. And of course, there you can go into any direction and the function values are decreasing. If you decrease the, let's say, the radius of the ellipse, then you are outside the constraint set. Of course, the function value is smaller, but the point is outside the constraint set. So the only way of having the minimum is that it touches this, our constraint set. And then we can compute for this constraint set or this function f, we can compute the cone of improving direction. So which is the direction where the function values are decreasing at this point? Okay, it's the same as the cone of feasible directions, because I draw here the tangent line. The function values are decreasing when I go into that direction. So it means that if I take this 0 point out, these two cones, so This point is the optimum point by our geometric intuition. So it means that the cone of feasible directions or improving direction for the cost function and the cone of feasible directions with respect to the constraints, their intersection is empty. They don't have common points. Okay, let's stop here. Okay, there were some questions in chat. No, the gradient of G1 I computed is 6 and minus 2. Okay, let's stop here, and on Monday morning we can really return back to and introduce this Karus-Kuhn-Tucker conditions for finding the optimal point of the constraint optimization problem. Okay, bye-bye.